Hi everyone. In this unit we'll talk about gases, but before we get into actual gases we will discuss the states of matter, all three states of matter: solid, liquid and gas. So this unit will be consisted of two chapters, chapter 13 and 14. So I'm going to start from chapter 13 today. We'll discuss states of matter. So, chapter 13 talks about the gaseous state of matter, the kinetic molecular theory of gases. We already know what a gas is. I don't think I have to explain that gas particles are very small. They take very little space compared to their size. They're too far from each other. They're not holding each other tightly. So there are no intermolecular forces. They have less density, because density is mass over volume. Since they are too far from each other, so within a certain space it is much less mass than a volume, so they are less dense. So particles particles volume is negligible, means you can simply ignore it. They are randomly moving in straight line, means they go here then go here. It means it doesn't go like this. Okay, that's what the straight line movement is. They move randomly. Okay, it can be anywhere, but it goes straight line. They're elastic, but this is what I'm explaining here is the kinetic molecular theory of gases. It is the theory of gases which is ideal gas. The scientists assume there is an ideal gas. But earlier on I was talking about the real gas. So in a real gas, particles of course are too far from each other, but they do take a space. It's not that they don't take a space, but yes, the space is very little compared to their mass. So we can ignore it, but we cannot say that it's they do not take a space. So we have to keep that in mind. And then it talks about the density of the gases. So as I was saying, the density of the gas is much less compared to the density of the solid, liquid, and solids and liquids. The particles are moving in straight line. Okay, they can have random movement, but they are moving in straight line. And then when they hit each other, okay, they exert a force. So they do exert a pressure. When they hit the wall of the container, they exert a pressure. When they hit each other, they exert a pressure, because force per unit area is pressure. So they do exert pressure, whereas scientists assume there is an ideal gas, not the real gas. In this situation, for the ideal gas, so they want to assume an ideal gas, and then they think that ideal gas should behave like this. So what they are saying is that in ideal gas, particles have no volume, like zero volume, which is of course not possible. But again, it is a scenario for an ideal gas, not the real gas. They also say when they hit each other or they hit the wall of the container, their collision is elastic. Elastic means no exchange of energy. They don't lose any energy, they don't gain any energy, which is not possible. Whenever you hit something, there is an exchange of energy. So, but again, as I'm saying, that this is the scenario for an ideal gas, not the real gas. Okay, so based on that ideal gas kinetic molecular theory, they have random straight line movement, elastic gradients. Particles neither attract nor repel each other, which is again not true. In the real gas, they have less force of attraction, but there is some force of attraction. At a given temperature, all gases have the same average kinetic energy. So what it is that it is possible that one particle is moving much faster than the other one. Okay, it's moving much slower. But when you take an average, you can say that since the kinetic energy is related to temperature, so if the temperature is the same, then the average kinetic energy will be the same. But that does not mean that every single particle in that gas is moving at the same speed. It is just not possible. Because when you have the gas particles in the container, this particle may kick this one and it can go faster. Okay, and the one that kicks it, since it has lost some energy, it will go back in the other direction with less speed. But as I am saying, the average is going to be the same. So you have to memorize these postulates of kinetic molecular theory of gas. Okay. Next thing we want to talk about is the pressure that I've been discussing. That whenever a gas particle hit another gas particle, they exert a force, and that force is called pressure. Okay, so force per unit area is called pressure. Pressure of a gas is from the particles colliding with the sides of the container and with each other. And the units for the pressure are three. I have ATM. Okay, ATM is a pressure, atmospheric pressure. ATM means atmospheric pressure. Kilopascal, kPa, kilopascal. Pascal was the scientist. And millimeters of mercury. Okay, millimeters of mercury. Mercury, liquid. So there are three units of pressure you have to memorize. You have to memorize that 1.000 atm is 101.3 kilopascal, okay, which is equal to 760.0 millimeters of mercury. So you have to memorize these units of the pressure. Okay, pressure, we can convert units from one another by using dimensional analysis. Let's say you want to convert 125 kilopascal to millimeters of mercury, so we use dimensional analysis. I have 125 kilopascal right here, so I know that 101.3 kilopascal, 101.3 kPa is equal to 760 millimeters of mercury. Millimeters of mercury. So kilopascal get cancelled. You multiply the two numbers and divide by this. That will be your answer in millimeters of mercury. So this is how you can convert units from one to another. But you have to memorize those standard values. So I have 650 millimeters of mercury. I know that 760.0 millimeters of mercury is 1.00 atm. Okay, so millimeters get cancelled. You multiply these two numbers and divide by this. That will convert your millimeters of mercury into atm. So this is how we will convert units. And you have to, as I'm saying, you have to memorize. This will not be given to you on the test or the quizzes. You have to memorize the standard values for the pressure, right? So speaking of pressure, there is a law that's called Dalton's law of partial pressure. Dalton is the scientist. This is the easiest thing that you will learn in chemistry, you know, Dalton's law of partial pressure. He said that if you have a mixture of gases, you know, 1, 2, 3, 4 gases, then the total pressure inside the container, because all of these gases are hitting the container and exerting a force that's called pressure. So the total pressure inside the container will be equal to the sum of the partial pressure of every gas. Okay, where N is the total number of gases in the system. You know, it goes up all the way to N. So examples, you have a mixture of 3 gases here. So you have total pressure should be equal to the pressure of carbon dioxide plus pressure of oxygen plus pressure of nitrogen, because these are the 3 gases we have in this total mixture. The question says that it has a total pressure of 0.97 atmosphere, you know, 0.97 atm. You have pressure of, what is the partial pressure of oxygen? You don't know the partial pressure of oxygen. You have the partial pressure of carbon dioxide and the nitrogen. So you plug those two in and calculate it for oxygen. You know, add them together and subtract it from this, and that's about it. That tells you the partial pressure of that gas. So it is, as I said, the easiest thing you can ever learn in chemistry. So the total pressure is carbon dioxide plus oxygen plus nitrogen. You had the 3 numbers. You just calculate one. That's about it. So you have to do these questions. We will do it in the class. So that's all for Dalton's law of partial pressure. So I will have a different video for IMFs. Thank you.